Mars is our neighbouring planet, or at least that's what we call it. But how close is it really? The answer is more complicated than you might think, because Mars doesn't maintain a fixed distance from Earth. Instead, the distance between our two planets is constantly changing as they orbit the Sun. Imagine the solar system as a giant racetrack. Earth orbits on the inner lane, faster and on a shorter path. Mars, on the other hand, orbits further out, slower and on a larger path. Sometimes Earth overtakes Mars on the inner lane, and it's precisely at these moments that the two planets come closest to each other. We call this favourable alignment opposition. At its best, when both planets are perfectly aligned, the distance between Earth and Mars is about 55 million kilometres. That sounds like an unimaginably vast distance, and it is. To put it into perspective, in a car travelling at a constant 100 kilometres per hour, it would take you over 60 years to cover that distance, which is almost an entire human lifetime. But on a cosmic scale, this is indeed the shortest possible connection to Mars. But it gets even more complicated. If Earth and Mars were on opposite sides of the Sun, that is, as far apart as possible, the distance would increase to a staggering 401 million kilometres. That's more than 7 times the minimum distance. Obviously, no one would launch a Mars mission at that time. The journey would not only be significantly longer, but would also consume enormous amounts of fuel. This is where a clever concept comes into play, one that space exploration has been using for decades: the Hohmann transfer orbit. Named after the German engineer Walter Hohmann, who calculated this trajectory as early as 1925, this transfer describes the most energy-efficient route to Mars. Instead of simply flying straight toward Mars, a spacecraft follows an elliptical path that elegantly connects the orbits of Earth and Mars. The idea behind it is ingenious in its simplicity. The spacecraft launches from Earth and accelerates into a transfer trajectory that resembles an elongated ellipse. This trajectory touches Earth's orbit at one end and Mars's orbit at the other. If everything is perfectly timed, the spacecraft will hit Mars precisely where it will be at the planned arrival time. You can imagine it like trying to throw at a moving dartboard. You won't throw directly at it, but rather where it will be in the future. The catch? This favourable alignment doesn't occur indefinitely. In fact, the ideal launch window for a Mars mission only opens every 26 months. This is because Earth overtakes Mars on its inner orbit approximately every 2 years. More precisely, it takes 780 days for the two planets to be in a similarly favourable alignment again. These 26-month cycles determine the rhythm of Mars exploration. NASA and other space agencies plan their missions years in advance to avoid missing these precious launch windows. Missing a window means waiting more than 2 years for the next opportunity, a delay that can cost billions and set back entire research programs. Interestingly, not all launch windows are created equal. Some constellations are more favourable than others, depending on the precise positions of Mars and Earth in their elliptical orbits. Astronomers and mission planners calculate the exact planetary constellations years in advance to determine the optimal transfer trajectory. Countless factors come into play: the precise position of both planets, the spacecraft's speed, the available fuel, and even the payload mass. Modern computer simulations calculate millions of possible trajectories to find the most efficient route. Sometimes, small adjustments to the launch date, even a shift of just a few days, can make a significant difference in the energy required, and thus in the mission duration. What does all this mean for the actual travel time to Mars? Well, even under ideal conditions, with a perfect Hohmann transfer during a favourable launch window, the journey to the red planet is anything but a short trip. But before we look at how long the journey actually takes, we need to understand which technologies can even get us there. One option would be conventional rocket engines. They are reliable, but slow. That's why scientists worldwide are working on revolutionary propulsion technologies. Ion thrusters are among the most promising developments. Instead of burning chemical fuel, they ionize a gas like xenon and accelerate the charged particles with electric fields. These thrusters are extremely efficient and can operate continuously for months. NASA's Dawn probe has already demonstrated how well this technology works. For a mission to Mars, ion thrusters could reduce travel time to about 4 to 5 months. Nuclear thermal propulsion systems are even more powerful. A nuclear reactor heats hydrogen to extreme temperatures, causing the gas to expand and exit through a nozzle. This technology is about twice as efficient as chemical rockets and could reduce travel time to Mars to 3 to 4 months. NASA is currently investing millions in the development of such systems. Nuclear electric propulsion systems go a step further. Here, a reactor generates electricity that powers electric thrusters, a combination of nuclear power and ion technology that operates even more efficiently. How long would a mission to Mars take with the technology available to us today? The answer may sound sobering, but it is the reality that space agencies currently have to work with. With conventional chemical rocket engines, the technology used since the beginning of space travel, a journey to Mars takes between 6 and 9 months. That's more than half a year in a cramped spacecraft, far from Earth, without the possibility of turning back or receiving help. It's a journey that places enormous demands on both technology and people. Chemical rockets work on a simple principle. They burn propellant and oxidizer in a controlled explosion. The resulting hot gases are expelled at high speed, generating thrust. This technology is tried and tested, reliable, and relatively well understood, but it has its limitations. The biggest drawback of chemical propulsion is its limited efficiency. Sending a spacecraft to Mars requires enormous amounts of propellant, and this creates a vicious cycle. The more propellant you take, the heavier the spacecraft becomes, and the more propellant is needed to move that weight. Rocket engineers call this problem the rocket equation, and it's the reason why massive rockets like the Saturn V or SpaceX Starship are necessary to deliver even relatively small payloads to Mars. Despite these limitations, we have already sent an impressive number of missions to Mars. The fastest of these was NASA's Mariner 6, which reached the red planet in just 128 days, a little over 4 months, in 1969. However, Mariner 6 was an unmanned probe with minimal mass. For crewed missions, which require life support systems, food, water, scientific equipment, and a safe return capsule, the calculations look very different. The Mars rover Perseverance, which landed in 2021, took about 7 months for its journey. The Curiosity rover, which arrived in 2012, was a similarly long voyage. These examples show that even with state-of-the-art technology, travel time stubbornly remains in the range of 6 to 9 months. But why exactly does it take so long? Several factors play a crucial role. First, there's the pure physics of orbital mechanics. As we saw in the first chapter, Mars missions typically follow a Hohmann transfer orbit, the most energy efficient, but not necessarily the fastest route. This elliptical orbit takes about 6 to 9 months, depending on how favorable the planetary alignment is at the time. Theoretically, one could travel faster by expending more energy and taking a more direct route. But that would require exponentially more fuel that would first have to be transported into orbit. The costs and technical complexity would increase astronomically. Another important factor is the payload. The heavier the spacecraft and its cargo, the more fuel is needed to accelerate it, and later to decelerate it. A crewed mission to Mars would likely weigh several hundred tons, including life support systems, supplies for the crew, scientific instruments, and the return module. Getting this mass to Mars efficiently is a formidable challenge. Acceleration also plays a role. Chemical rockets can only deliver short, intense bursts of thrust. After launch from Earth, there are typically few opportunities for corrective burns, brief engine ignitions to adjust the trajectory. For most of the journey, the spacecraft glides through space without propulsion, carried by its initial velocity and the gravitational forces of celestial bodies. This is where gravity assist maneuvers come into play. Clever tricks that utilize the gravity of planets. A spacecraft can fly past the planet and steal speed without using a single drop of fuel. These maneuvers, also called swing-by or gravity assist, made missions like Voyager 1 and 2 possible. They are used less frequently for Mars missions, as direct Hohmann transfers are usually more efficient, but they remain an important tool in the mission planner's arsenal. The reality is sobering. With current technology, astronauts on a Mars mission are confined to a relatively small spacecraft for at least 6 months. They are exposed to cosmic radiation, experience weightlessness with all its health consequences, and have to make do with limited supplies. It is one of the greatest challenges humanity has ever undertaken. I sincerely hope you enjoyed the video, and perhaps you now have a new perspective on the Mars mission and its complexity. I also made a video about why people who go to Mars probably won't be able to return to Earth. Feel free to watch it, and I hope to see you next time.